the third page here where it says matrix multiplication. On that number 1 practice, what are the dimensions of number 1? What? 2 by 3. A 2 by 3. Excellent. And a 3 by 2. Can they be multiplied?
Yeah.
Yes. What should your answer be?
2 by 2.
A 2 by 2. So your answer there should be a 2 by 2. So right away, you should be writing brackets with 4 empty spaces for it. All right, number 2. What are the dimensions of number 2? 2 by 2 multiplied by a 2 by 2. So your answer will be 2 by 2. Awesome. Okay, so turn it over on the back. What should your answer be for number 3? What size should your matrix be? A 2 by 2, right? Number 4, we have a 2 by 2 multiplied by a 2 by 3. So your answer should be a 2 by 3. Excellent. Number 5. What's number 5?
Finally, something that's unstoppable.
Okay, why?
It's a 2 by 2 and a 3 by 2.
A 2 by 2 and a 3 by 2. So number 5, you should write
Undefined.
not defined. You cannot multiply it. The inner numbers did not match. We had a 2 by 2 and a 3 by 2. We cannot multiply those together. Okay. Number 6 should be, it's a 2 by 2 multiplied by a 2 by 2. So we end up with a 2 by 2. The answer should be a 2 by 2. All right. So there are going to be parts of 4.3 that we're going to cover, and then parts we're going to leave out. There's some terminology that needs to be in a different order for that, all right? So they're going to start talking about, okay, the one thing that you do need to know is that, remember when we talked about all of our rules, our regular math rules? So we've got community property, associative, distributive, we've got identity, and we've got inverse. What did identity do? For any number, the identity means that it is the same. It's itself. Remember, identity is who you are. I talked about it as looking in a mirror. When I look in the mirror, I reflect back myself. So an identity for an addition, how do I get, what's the identity number for addition? 0. So the identity for addition is always 0 because it's the number that reflects back myself, right? The identity for multiplication is the number what?
Times 1.
1, because 1 is the number that reflects back myself. So in the same way that we used identity with our addition and our multiplication, identity means the exact same thing with the matrix. It is the matrix that simply reflects back yourself. So you're going to end up with the same one. And the identity matrix has 1s along the diagonal and 0s everywhere else. See how 1s are important? So it's interesting because we use the same numbers. We have 1s and 0s there, okay? I think I do have, I think it's at the end. Here we go. Okay? So for a 2 by 2, we have 2 1s. For a 3 by 3, there's 3 1s. For a 4 by 4, there's 4 1s. Okay? Identity means you're simply going to reflect back itself. When you use an identity matrix and you multiply it times any matrix, your answer ends up the very same matrix that you started with in the first place. You're just reflecting back. You're getting the same answer there. Okay? The other option is an inverse. Okay? So when we had regular equations and we wanted to have an inverse, we said the inverse is the thing that causes you to have no change, correct? No power to change. When your parents give you the inverse answer of you're wanting to go out and they tell you no movement's happening, right? So the inverse for addition either gets us back to 0 because 0 gives us no power to change. For multiplication gets us back to 1 because 1 changes nothing in multiplication. So the inverse in addition here would be -4, correct? The inverse for multiplication would be 1/4. So the inverse is whatever we are either adding or subtract or multiplying by that gets us back to the value that has no power of change. So with matrices, there is a specific inverse as well, and it's to get us back to the number 1. Okay? The way we do that is we need to know certain information first. So that's where we're going to head, and this is the information that we need to know. It's called the determinant. Okay? So you have on here, it says determinant, a scalar value. Again, they're just using new terminology. Scalar just means a number, right? A number that is computed from the elements of a square matrix. Says the determinant of a matrix is denoted by DETA, or A inside what looks like absolute value signs, right? This does not mean absolute value. This means the determinant if it has A, okay? And so A is our matrix, and people will talk about what's the number inside the matrix. Like, which is a decent movie, if anyone has. You guys might be too young for that, okay? So for number 1 here, if you have a 1 by 1 and you only have the number 3 inside, your determinant is that number. It's 3, okay? But when we have extra ones, there is there's a formula that we have to use. And in this case, if we have it labeled A, B, C, D, we're going to work with the diagonal. So we've got A times D. We're going to subtract B times C. I like to think of it in terms of time. AD is present time, right? BC, before Christ. So present minus the past lets us know where we're at. It just helps you like remember which ones go together if you get random variables together. But the way that we do that is we are always going to work from the left to the right, and that's going to be our positive. Just if we, same as if we had a coordinate plane or a number line, when we move from the left to the right, we go towards the positives, right? And if we move from the right to the left, we have what?
Towards the negative.
We have negatives, right? So if we move from the left to the right and I multiply A times D, that's going to be my positive term. If I move from right to left and I do B times C, that's going to be my negative term. Right? So the way that we work this out, there's some examples up on the board. So for the first one, we have -3, 2, 5, and 8. So the first thing that we're going to do, we always start in the upper left-hand corner. So we always, again, we start left to right, and we always work top to bottom. So as long as you keep left to right, top to bottom, you can keep everything in order. So we're going to go left to right, down towards positive. So we're going to have -3 times 8 is going to be our first one. Then we will subtract, and we're going to, again, start top to bottom, but we're going backwards. So now we're going right to left, which on a number line makes us go negative, right? So there's our negative sign. 2 times 5. 2 times 5 gives us a 10. So I had -24 minus 10. So we end up with -34. So the determinant of our first matrix, we don't see that number -34 in there, but the value of it is -34. Right? For the second one, we've got 13, 4, 8, and 2. Again, we start at the upper left. We're going to start left to right. 13 times 2 gives us 26. We're going to put a big subtraction sign. The subtraction sign is not dependent upon these numbers. So it is okay to do this or to do this as we get into the 3x3s, which I think we have just enough time to cover. This subtraction sign must remain. So you'll have everything moving left to right in our first brackets and everything moving right to left in our second, and the subtraction is in the middle. Which means, what happens here? You either need to distribute that negative or work everything inside your brackets first and then subtract it, right? So for the one that's up here, we're going to multiply our 13 and our 2. We're going to subtract our 8 times 4, and we get the number -6. Okay. Steps for a 3x3 to find the determinant. Okay, just enough time. I'm going to work with numbers. Okay. When we have a 3x3, the answer will still be a single number. The determinant will always be one single number. Every single time, right? Because it can get really tricky to figure out which numbers you're supposed to multiply, when you're doing anything bigger than a 2x2, you are going to rewrite your columns outside of your brackets. And again, we start left to right. So this is column 1, 2, and 3, and I'm just going to start back over, and I'm going to write them again. So I'm going to rewrite column 1. I'm going to rewrite column 2. Okay. If I had a 4x4, then I would rewrite column 3. Okay, we're going to keep going until we have the same number of terms in all of our diagonals. So see, our first one that we worked down has what? It has 3 terms. 1, 2, 3. That means as I work down, I need to have 3 terms. So if I had not written this second column, I would be missing a spot here on the bottom. If I go ahead and add the 4th one, well, this one's not included. Do you see? So we want our arrows or our columns to come out exact. We want it to be nice and pretty. Right? Another hint is if you have 3 columns, you will rewrite 2. If you had 4 columns, you would rewrite 3. If I had 10 columns, I would rewrite 9 of them. Okay? So as we do that, again, we're using the same rules of 2x2s. We're going to start in our upper left. We're going to go diagonally down until we hit the bottom. We're going to multiply all of it. Right? But in this case, everything that we now have is we now have 3 things that are moving from left to right in our positive direction. So I'm going to have 3 separate terms in that first section. So my first one, as I move down, it says AEI. So I've got 2 times 0 times 4. So I have 2, 0, 4. It goes in this first place, which gives me a 0. It's great when there are zeros in there. The second one, I've got -1, 1, and 1. Gives me -1. My third one, I have 3, -2, and 2. 3 times 4 is 12, and it's negative. Okay? Don't lose your signs in the midst of the thing of all of the addition. Right? So that's everything left to right, moving in a positive direction. Now we have our subtraction sign. Our subtraction sign is subtracting everything that is going back the other direction. Okay? So now we're going to move right to left, and we're going back doing the exact same thing. So we start at the top, and we're going to move down diagonally through all of the numbers. So our first one, we multiply all three of those numbers, -1, -2, and 4, gives us a positive 8. We've got 2, 1, and 2 gives us a 4, and a 0 again. Now the thing to note is that when we are grouping all of our negatives, or all of our diagonals that are going towards the negative, they are still added together, right? So everything that goes left to right is added together. Everything that goes right to left is added together, but the entire amount is what is subtracted. Okay? Does that make sense? Okay. So I highly recommend to bracket your sections together. That way you can keep everything added in the midst of it, and then we can subtract it separately. All right. So I will post up your homework. I will also post some individual videos breaking this stuff up for it. And then next week, we will start figuring out how is this useful with anything.